Hello everyone, I am Saidur Rahman. Today I am going to present our paper short and sweet checkpoints for CRAN mobile edge computing. Here are the authors information. We know that mobile edge we know that a user device have limited computation storage and battery capacity, so user device need to offload the task to the nearby servers. If we consider cloud, in that case the round trip time between user and the cloud is high, so user need to offload the task to the edge server, which is deployed near from the user. If For low latency services, if the user use like 5G and mobile edge computing services, they can get like very low latency services. Here is the like basic high level architecture of 5G, where uh, we have the 5G core connected with BBU pole, and under the BBU pole we have multiple BBUs, which is also connected with multiple remote radio heads. uh, each BBU have like mobile edge computing node, and they are sharing the same physical resources. And BBU uses resources for network traffic processing, and mobile edge computing is using the resources for computation and other edge services. So when the network traffic grows, more BBU needs more resources to handle the network traffics. In that case, when the resource is not available, in that case BBU needs to share the MEC resources, MEC resources to get more resources to handle those traffics. The thing is, for example, in the MEC resource, one task is running. In that case, to free the resource, we need to turn off the turn off the task. And we need to migrate the task to the same node or maybe in the different node, based on the based on the scheduling. So in that case, if we turn off the task and the task is long running stateful task and running for some times, if we stop the process, stop the task without saving the states, in that case, if we after migration, if we rerun the task again, we need to actually run from the beginning, not from the last point we stopped. So that's a problem. It ran for some time, so we wasted the resources, right? So in that case, we need a solution to handle the scenarios. That's why we propose micro lambda framework, that is that handles the scenario we describe. For example, this is the process F process that takes I input and shows output I, and the total runtime, for example, is R actual. And this is a stateful process, and we have like n number of state, for example, S1, S2, Sn, and so on. So for example, after R limit, that is the less than actual R limit. So after R limit, for example, the BBU needs to share the application. In that case, there is no way we can if we stop the process without saving the state, we have to rerun it from the beginning, right? So in that case, that's issue. So for micro lambda, we took the idea and we implemented such a way. For example, in a serverless platform, for example, we have the lambda function with we deploy the if inside of a lambda function we have a R limit. We can say after R limit we will save the state, and then we can rerun the lambda again with by loading the state one and run the one, and so on. After some execution, we take the last one, for example this Sn, and then we process this. So this is done, so we have the final output. So if you see that, it's look like the same. We are running from here, after taking the input, we're running, and at the end we are showing the output. In the back end, we are storing and restart the app based on the scenario. So it's like the same we are doing the actual one with saving the states. So how? Here is the pipeline how we can handle the thing, because we are using serverless platform. So in that case, we have a client, we're sending the request to the Redis server that gets the request and notifies the manager. As it's a serverless architecture, we have manager worker node, so it notifies the manager that one request has come, and manager will find the available worker, and the worker will actually the available worker, and then my manager will invoke the Lambda with the worker, and the worker starts working until the R limit. After the R limit, it saves the state and notifies it saves the state to the Redis server, and Redis server notifies the manager the task is done. The manager will again check that the task is completely done, or we still need to complete. So it finds that we need to rerun again with the new state. So it will invoke the same worker or different worker again, and worker will download the previous state and does the computation and save and so on. After some iteration, when the task is done, the Redis will get the output and notifies the client that here is the output. That's the step we are working. So how we implement the checkpointing here, so that we can save the state. So for example, this is the traditional application where we have, for example, 8 number of lines. For example, currently it's running the line 5, and now it will go for line 6, and then so on 7 and 8. But for our micro lambda, when we deploy the application, in that case, initially we added some lines before running. We added the line using the Python abstract syntax tree. So our micro lambda is for Python based Zephyr framework. So the checkpoint resume is when we run the program, the checkpoint resume will run first, and it checks that is there any previous state available. No, initially we don't have any previous state, so it will actually run from line 1 and so on. For example, after line 5, our R limit is done. Its R limit is a variable here. So after R limit, the micro lambda will inject some of the codes inside of the running script using Parasite. It's a library for injecting injecting binaries or codes to a running program. So it saves instead of running to the line 6, it will save the state, upload the state, and terminate the process, so that what it saves actually as the Python is the interpreter, so it saves the Python stack information of my Python object stack. So we have and in the stack has the information that which line is executing, which the last line we executed. So then next time when we rerun the program again, the same worker on a different worker, they will download the checkpoint state, and when they rerun the program again, the checkpoint resume will get find that we have a checkpoint, we have a previous state available, so it loads the previous state and jump from here to line 6 and so on, then we'll continue the execution. So that's how we are saving the states and resume the states. So for verifying the system, we are actually using 3 different applications: face recognition application, ride-hailing application, and stress classification application. Face recognition application is compare two consecutive images to find the similar face. Where for this computation, we use machine learning library, which is called dlib, and that compares the faces and to respond based on the result. And we have ride-hailing application, which is actually Uber, where the ride-hailing application actually allows the client to request for the nearby taxi in a geographical location. For this, we use the shortest path algorithm and shortest time analysis algorithm. In that case, we use the real data set, New York taxi data, where we have the real driver and client location, and we analyze based on the we analyze based on the data point and the availability. We have another one is like stress classification, where we have like we classify the mental stress based on the human physiological signal. We extract the extract the feature from the human physiological signal, like such as heart rate variabilities, and then we using the machine learning model, we predict predict the stress or no stress. So, and we also compare the complexity of the application. You can see that here it's the for this application with the input, it hits 24,000 number of unique lines, and here it hits 7,000 more than 7,000 unique number of line it hit when they do the computation, and this is like 102,000 number of unique line it hit. So we compare our micro lambda framework with the CRIU, which is the current existing Linux-based checkpoint and register in user space. CRIU actually freezes the running container or individual application and checkpoint the state to the disk. CRIU takes the PID as the input and saves the process information such as memory pages, file descriptor, and inter-process communication and other information for the process. And that's why this CRIU actually saves a lot of things, as I state. So that makes the overhead very heavy. I will discuss the comparison in the next few slides. So in this experiment, we use edge cluster, and for that we use Docker Swarm, and we for the serverless platform we use OpenFaaS, and for 5G simulation, the client manager workers, we use ContainerNet, which is a Docker-based mininet. So for the first analysis, we compared the CRIU and the micro lambda for checkpoint time, which is like time to do the checkpointing, and the checkpoint size. Where you can see the x-axis we have the application information, and the y-axis you can see checkpoint time and the checkpoint size. For both figure, you can see that the micro lambda performs very good, because like it has a lower overhead compared with the CRIU. Similarly here, for the checkpoint size, you can see that micro lambda has very low overhead compared with the CRIU, because like micro lambda saves the like Python stack information and as least, so, and it is also compressed, so that makes it very low overhead, and but CRIU saves a lot of things, so that it takes more time to store the checkpoint, and it also it makes the checkpoint heavy. In the next graph, we actually explain about execution time, where we have we show two different graph. We have another graph, we didn't show it here. If you want, you can check our paper. So in the x-axis, we increase the workload, the number of images, number of requests, and y-axis we have the execution time in seconds. Here we compare micro lambda with CRIU for different R limits with the long running process. You can see that long running process has very low execution time, because it doesn't save any checkpoint, and we don't need it doesn't need to stop, rerun again, migration, everything. We don't long running process doesn't do this thing, but CRIU and micro lambda does this thing. So in that case, you can see that CRIU has higher execution time compared with micro lambda. These both have the same R limit too, so micro lambda performs better than CRIU. Similarly, in the second graph, you can see the same result. Micro lambda perform better compared with the CRIU for all cases. Here you can see that this is a face recognition application, where we increase again the number of images, number of requests here for network load. We in the y-axis we have the network load, and you can see that here is still my CRIU performs bad, because CRIU has higher overhead, so it takes if we offload the checkpoint, it creates more network load compare with micro lambda. Similar happened with the second graph ride hailing application. CRU performs bad. In this application, in this paper, we actually propose micro lambda framework to partition the application execution across the runtime. It allows the dynamic splitting for stateful and long process computation across the multiple serverless invocation. That's all we did in our paper. In future, we can have multiple option. We can make the Python extension to with the CRIO. Like if someone asks like why I am injecting parasite to make, it can be virus. It like we are injecting it, that's like that can create a security issue. That's why we need Python extension for CRIO that will make keep us the security. We can also work with the incremental checkpointing that actually to minimize the checkpoint rewrite. So if we need to find the common checkpoint that we can skip, we just need to track the changing part of the checkpointing. We can just upload this so we can minimize the overheads. We need to also do the scheduling decision using using checkpointing when BBU starts shading. For example, like when I need to migrate the task that I stopped. That we need to make those scheduling decisions based on the scenario. So that's we can do in future. That's all I have. If you have any question, feel free to ask.